So, in this session we are going to discuss about the PVT behavior or the phase behavior of a pure component, and subsequently we will be discussing about the equation of states, and that includes virial equation and cubic equation of states, which will be followed by the discussion regarding two parameter theory of corresponding states, and additionally, as you know, the three parameter theory of corresponding states. So, to start with, we have to understand the phase behavior, right, of a pure component. So, this will be a discussion of the PVT phase space and the profiles associated profiles in this PVT phase space. So, instead of going for this three-dimensional PVT phase space plot and the profiles, we will concentrate on the PV and PT phase space or phase plane rather. Okay. So, there we will qualitatively try to understand and describe the behavior at the different isotherms, how it looks like, and thereafter we will switch to this how to describe their behavior through some quantitative functional relation between pressure, volume and temperature. So, these are the equation of the states. Okay. So, behavior of pure species in PVT functional form or PVT phase space, right. So, first it will be a PV diagram, right. Before you go to this description of this PV diagram and the different isotherms, let us again just state that degrees of freedom at any point will be this C minus P plus 2. So, obviously 1 minus 1 plus 2, so it is 2, right. So, it has got 2 degrees of freedom anywhere on this PV space, right. But if it is on the saturated liquid line or saturated vapor line, that is vaporization curve or this saturated liquid plot, right. So, there it will change. So, at triple point, see degrees of freedom at triple point. At triple point we have 3 phases to coexist. So, it is 0. On degrees of freedom on any boundary line or any this line separating 2 phases will be definitely this C. C is basically 1, phase is 2 plus 2, so it is 1. So, it continuously go on changing. So, if it is any arbitrary point in this PVT space, so it has got 2 degrees of freedom, whereas if it is a triple point, it has got simply 1 degree of freedom, and if it is any line, a point on the line of this phase change, so it has got the degrees of freedom equal to 1, right. So, with that basic understanding, let us describe the PV space, and we will try to describe it through the pattern of isotherms. There is constant temperature lines, right, because we have 2 variables, pressure and temperature. So, we have fixed the temperature, pressure and volume, we have fixed the temperature. So, it will be giving you a line, right, because you see that degrees of freedom is 2. So, essentially as we are fixing the temperature, so degrees of freedom reduces to 1 and its dimension will also be 1 and that is why it will be a line. So, if at a temperature less than critical temperature of that system, and critical temperature is something you see that T greater than Tc, we do not have, for T greater than Tc we do not have any difference between liquid and vapor, right. So, for T less than Tc, where liquid and vapor they are distinguishable, what will happen? So, on the left hand side, extreme left hand region of this plot will have a liquid region. Now, liquid, you know, it is a highly incompressible state of matter, right. So, this region will be liquid region. So, it is highly incompressible. That is very low del V del T del P at constant T, right. So, for a wide change of pressure, it is expected that we will have a very small change in volume. So, the graph or the line or the isotherm looks like this. Okay. Now, once the liquid, see it is a constant temperature and we are from a very high pressure, we are reducing the pressure. So, volume slightly increases and at a certain point it will be saturated. So, once it is saturated, further if you try to reduce the pressure, there will be no pressure reduction unless there is a phase change, right. Because from here, this is the point, this is the subcooled liquid region, subcooled liquid, at this point it is saturated liquid, and now further if you try to reduce the pressure will not change unless it is fully vaporized and transforming itself into a saturated vapor moving through a two-phase region, right. So, that represents the phase change. So, it will be like this. So, here we will have saturated vapor. Now, further if you reduce the pressure from here, again the pressure reduction is allowed, and further if you reduce the pressure, definitely it will be a superheated vapor. So, that is the vapor phase. And here the slope is relatively much lower than that of the liquid. Okay. So, del V, or rather if we write this del V del P at constant temperature for the liquid phase, right, is much lower than del V del P at constant temperature for vapor phase, or rather the gas phase. Okay. Gas and vapor, they are distinguishable in terms of their critical temperature, right. So, in general we will call it a vapor phase or gas phase, whatever. Okay. Initially we can use these two terminologies analogously, however above and over critical temperature, and that will be better described in PT phase space. Okay. So, anyway, so this is a vapor or a gas. So, this is the point of saturated vapor, and this we are doing this experiment at a temperature T1 and T1 is less than Tc. Okay. Now, if you repeat that experiment at a higher temperature, a bit higher temperature, what we will see? That the change of volume actually reduces, right. The change of volume reduces from the saturated liquid to the saturated vapor. So, the curve looks like this. Okay. So, and finally, at the point of criticality, it will be like this. So, this two-phase region reduces to a point. Okay. Two-phase region reduces to a point, and that is the critical point. See, this is critical point. So, we can isolate a region of two phase if we go on connecting this line to critical point, and on this side this line. So, this is liquid plus vapor, this is the liquid side, this is the vapor side, and further. So, this is at Tc, say this is at T2, and further if you go on increasing, there will be no inflection and the curve will be looking like this. Okay. So, this is the vapor phase, and above and over this vapor phase we have the gas phase, okay, because gas is a state or vaporized state above and over this critical point. So, here you see that how to identify the critical point if I am given with a relation of this. Okay. So, critical point property. What it will be? It will be simply as C is a point of inflection, we have first and second derivative must vanish. So, del P del V at Tc equal to del square P del V square at Tc, that must be equal to 0. So, this is the condition for the critical isotherm. At this critical point, this del P del V and del square P del V square at Tc, or at, rather let us write at critical point. So, it is C, it will be equal to 0, and this is the critical isotherm. Is called the critical isotherm. So, this is the two-phase dome shaped two-phase region, left hand part is a liquid, right hand part is a vapor. So, this is the saturated liquid arm, this is the saturated vapor arm. So, over this line everywhere up to critical point we have saturated vapor, and on this side it will be saturated liquid. Okay. So, that is about the PV space and the respective isotherm at this PV space. So, next more elaborately, though we have discussed it in this phase change and discussing when we have discussed this Clausius-Clapeyron and Clapeyron equation, there we have discussed this PT, but again we will elaborate the idea. So, PT diagram. Now, you see PT diagram is more fundamental and it looks like this. So, here this where the three phases coexist, this is the vapor phase, this is the liquid phase, this is the solid phase. So, the three phases coexist. So, this must be the triple point. Right? This is the critical point. And the vaporization curve exists between the triple point and the critical point. fusion curve is indefinitely being stretched in this direction. It is because solid and liquid are always distinguishable. So, that is the fusion curve, and the phase change line or the boundary between the solid and vapor is obviously the sublimation curve. Right? Now, above and over this critical point, we have the supercritical fluid, or alternatively called the fluid region. This is precisely the supercritical fluid. Right. Now, here we will try to understand the difference between vapor and gas. So, when the temperature is below this Tc, it is the vapor phase, and alternatively when the temperature is above and over this Tc, it is a gas phase. So, that we have studied from our school days. Basically, you see that what is the differentiating mark between the vapor and the gas? Vapor can be transformed into liquid at a constant temperature simply by pressurization, right, which we cannot do for gas. So, here you see that if I think of an initial state A, we increase the pressure, you will get the liquid, right. However, here if we go on increasing the pressure, we will enter the supercritical fluid region of the fluid phase, however not liquid. For liquid, we have to basically reduce the temperature. Okay. So, how the gas can be liquefied? We have discussed it. First, the gas is to be cooled and then you pressurize it. First, the gas is to be cooled and then we have to pressurize it, or we can do it alternatively. We can go for first pressurization and then cooling. Okay. That can also be done. First you are pressurizing it and then cooling it. So, you see, this is the idea of this vaporization curve and the respective phase transition, and in relation to that, what is the difference between the gas and the vapor phase. Now, what is more important that you see, we can change the phase from vapor to liquid without actually any phase change, and apparently it seems to be an absurd statement. However, if we think of a path from A, if I move like this, there is no phase transition because this dotted line is not crossing any phase boundary. But we are moving towards the fluid region from this vapor phase, and from the fluid region again we are reducing the temperature, that means we are cooling it, right, and we will be getting a liquid. So, without any phase change we can transform the vapor phase to liquid phase. So, visually you cannot sense any phase change. Everywhere the pressure and temperature is not changing, everywhere the pressure and temperature they are changing, which is just opposite to that of phase change, because we know during the phase change pressure and temperature remains constant. So, we are continuously and progressively changing the pressure and temperature, and finally we are going to this liquid phase. Okay. Now, regarding the fusion curve, what we have discussed previously, you see that dp sat dt from Clapeyron equation, dp sat dt equal to delta H alpha beta divided by T into delta V alpha beta. So, this is the relation for universal relation for all these, or equation for all these lines: vaporization, sublimation and fusion. Now, when you see that when we are transforming a solid to vapor through sublimation, the typical example is camphor, right. So, what we will observe? That the latent heat is always positive, and the change of volume, molar volume, that's also always positive, because vapor volume is obviously much higher than that of the solid volume. So, dPsat dt is positive for sublimation, right? And dPsat dt is also positive for fusion except water, which exhibits anomalous expansion as delta V LV, which is here delta V SL, which is liquid minus solid, that's negative, right? When ice melts, the volume actually decreases. Okay. So, liquid volume here is lower than the solid volume, and as a consequence we will have for water, this will be the nature of the curve. Fusion curve for water, right? Now, regarding vaporization, we have this Clapeyron equation, and also over this narrow region, maybe over here, we can use this Clausius-Clapeyron equation. Which states that d ln Psat dt, d of 1 by t, equal to minus of delta H LV by R, right. So, the slope is actually, the slope of this dPsat dt curve is actually positive, because this, if we split, it will be dPsat by t, and this will be minus of dt by t square, as you all know, right. So, this is minus of delta H LV by R, and the minus and this minus cancels out. So, we have dPsat dt positive. dPsat dt is positive because this is equal to delta H LV by RT square into this Psat. So, you see the slope here is dependent on the pressure, and essentially it gives you nonlinear profile, right. So, vaporization curve is nonlinear, whereas fusion curve is more or less a straight line, as this delta V SL, right, it really changes with this pressure, and similar is true for sublimation curve. Fusion and sublimation, these two are linear nearly and actually they are linear because with the change of this pressure, right, with the change of pressure the temperature changes linearly. The reason is this part is nearly constant. This part is nearly constant, so sublimation curve is linear, it is independent of Psat, so it is linear. The fusion curve is also linear, however vaporization curve is nonlinear. So, that is the idea of this PT diagram. Now, our objective is to describe this behavior of PVT, right, through certain equation. And if we know from the kinetic theory that the model is basically of ideal gas, right, where we know that the simplest model of this pure species equation of state is the ideal gas equation. So, fundamentally in kinetic theory, we have two assumptions. The first one, volume occupied by the gas or by the material is negligibly small occupied by the molecules, volume occupied by the molecules is negligibly small compared to its own volume, that is V, and second, no interactions between molecules. Right? Now, the low interaction necessitates that the intermolecular distance between two adjacent molecules, the mean intermolecular distance must be pretty high. And you see that R, that is the intermolecular distance, is in the order of V to the power 1/3. Right. So, for an ideal gas model, which the real gas will actually tends to that behavior, we must have a very high volume, right. That means respectively it is a very low pressure according to the nature of this PV space. So, the pressure must be low, right, and it is observed obviously there is an expansion of material with enhanced thermal state. So, the temperature must be very high. So, for these isotherm which is much above and over the critical isotherm at a very low pressure somewhere here, we can actually consider the real gas is tending towards the ideal gas behavior. So, pressure must be very low and temperature must be high, right. So, these are the physical conditions to have large intermolecular distance, and as we know this intermolecular interaction decays with R to the power 6, right. So, it is basically this sort of profile. So, intermolecular interaction energy versus distance. So, this is called the Lennard-Jones potential model, right. So, in this model you see that as we are going on increasing the distance between the molecules, it tends to 0, right. There is no interaction at all, because both the attractive arm and the repulsive arm, that both decays with the distance. So, the attractive arm, generally this E, we can model it as A divided by R to the power n plus B divided by R to the power m. So, this is the general model. Then n is considered to have a value of 6, right. So, the attractive interaction rapidly decreases or rapidly decays with distance, intermolecular distance. So, if you increase the volume, so intermolecular gap will be increasing, right, and as a consequence the intermolecular interaction will also be nearly 0, and the volume occupied by the gas molecules will be negligibly small compared to the volume of the gas. Okay. So, essentially the first and second condition is being satisfied closely when we increase the volume and also increase the temperature. So, increasing volume means you are actually reducing the pressure. So, pressure must be very low and temperature must be very high for a real gas to approach towards this ideal gas behavior. Now, you see that in order to describe this ideal gas behavior, we can directly start from this Charles law and Boyle's law and all what we have studied from school, but we will not go by that. Okay. We will try to fetch out that what is the physical meaning of this universal gas constant, and from there we will try to describe the equation for real gases. So, ideal gas equation, you see what is the significance of R? If I plot PV by T versus say P, right, we will see that the data points, if we do the actual experiment with gases, it will be either it will look like this or it will look like this. Right. Now, if I join them by a smooth graph, the best fit curve, it will be converging for 0 pressure to a universal value, and that is R, right, for 1 mole. Like what I tend to mean to say that limit P tending to 0, PV by T is equal to R. Right. From this graph, we can interpret that PV by T is a limiting condition, P tending to 0 tends to R. So, what is R then? So, we can say that it is a limiting value of PV by T. Now, what is PV by T then? Just as we do not know anything here, let us go for a dimensional analysis. This is force per unit area multiplied by volume, right. So, it is force into length dimension, and that is actually energy. So, energy per unit temperature, okay, energy per unit temperature per unit mole. So, dimension of R should be energy per unit mole per unit temperature. So, that is R, okay. So, as temperature increases, the energy per unit mole for this ideal gas model must increase, and from kinetic theory, you see, energy of 1 mole of gas, what do we know? That E is equal to 3 by 2 RT, right. So, R is the order of energy for ideal gas. So, order of that energy is RT, or R specifically indicates that it is order of that energy is RT. So, this this is the order of that energy is RT. So, this R is the order parameter coupled with temperature, right. R is the order parameter of energy which is coupled with temperature, okay. So, from there it is clear from the dimensional analysis, it exactly corroborates with the dimensional analysis that energy per unit mole per unit temperature is basically R, and as you all know that its value is 8.314 joule per mole per Kelvin, okay. So, that is about the ideal gas. Now, question is this part. So, here close to this it is an ideal gas state approaching towards ideal gas state, but here in this region we have real gas. Now, why the real gas behavior is deviant from that of ideal gas? Definitely the interaction comes into picture, and the volume of these gas molecules will no longer be negligible compared to the volume occupied by the gas, specifically if you go on increasing the pressure where the volume reduces. So, one of the very obvious idea is that the PV by RT equal to 1, right. PV by RT for 1 mole is equal to 1. So, this is the ideal gas equation. And it is having no interaction at all, no interaction between molecules, right. Now, if I am trying to consider this two body interaction, right, and this is a kind of energetic term, PV by RT, that is a dimensionless form of energy. Okay. So, PV by RT we call Z, and that is the compressibility factor, which is 1 for ideal gas. So, when we consider this two body interaction, we have to add on dimensionless energy terms, right. So, you should go on adding dimensionless energy terms. So, though the exact theoretical background comes from statistical mechanics, but we will not discuss this. So, our objective will be that okay, PV by RT equal to 1 for ideal gases. For real gases, we can write this PV by RT as a polynomial expansion of this 1 by V or P, right. So, accordingly we have B by V plus C by V square. C by V square is a 3 body interaction term, plus d divided by V cube, it is a 4 body interaction term, so on and so forth, right. Such that if we do not go for, if the pressure is low to moderate, we can truncate this term here, and the equation becomes Z is equal to 1 plus B by V. If we consider 2 body as well as 3 body interaction term, we have to include this. Okay. So, for this is the form of real gas equation for low to moderate pressure. Right, and this is the introductory idea of V-real equation. So, this is the V-real equation, or rather the volume explicit form of V-real equation. We can also write this pressure explicit form as 1 plus B prime P plus C prime P square dot dot etc. So, you see this observation, and we can justify it via statistical mechanics, that V-real coefficients are functions of temperature only. Okay. V-real coefficients are basically functions of temperature. So, and there must be, this is the pressure explicit form, of V-real equation, and these coefficients, we can derive a relation between these coefficients, like P, you see P is equal to this ZRT by V plus C prime ZRT by V whole square and so on. So, if I write this B prime RT by V and Z the volume explicit form B by V plus C by V square etc. plus C square C prime RT by V square RT square, and here we can write 1 plus B by V plus C by V square etc. So, 1 plus B prime RT by V, the first term, because there is no other terms having a denominator of V, right. The second term will be this giving a V square. So, it is B prime RT into B plus Here the term is, the first term basically, even if we expand, the first term will be 1, right. There is no other term because all of the terms will consist of additional 1 by v multiply, the exponents. So, it is c prime RT whole square divided by v square, so on and so forth. Now, if I compare this form with this form, what I will get? B is equal to B prime RT. So, B prime, the pressure explicit form, can be written as B by RT. Now, B prime RT plus C prime RT square is equal to C. Okay. Now, B prime is equal to B divided by RT into RT plus C prime RT whole square is equal to C. Right. So, C prime is equal to C minus B divided by RT whole square. C prime becomes C divided minus no, here we have B prime RT, B prime, this B I have missed, I think, this B is there. So, B square C prime minus B square divided by RT whole square. So, similarly you can calculate this D prime in relation to this B, C and D and so on and so forth. So, these coefficients, we can interchange them. Interchanging means here what we can write, that we can write Z is equal to 1 plus B by RT into V, right. B by RT into P plus C prime we can write as C minus B square divided by RT whole square into P square. So, we can interchange the coefficient and can write it in this form as well. And this form is preferred over the pressure explicit form because the volume explicit form's coefficients are more fundamental than pressure explicit form's coefficient. Why? Because you see the two body interaction, that V is proportional to intermolecular spacing to the power 3, right. Volume is proportional to R to the power 3. So, this gives you an equation which is very similar to this interactive energies form, like E is equal to minus A divided by R to the power n plus B divided by R to the power n. So, in terms of volume, actually we can replicate the order of intermolecular distance, right. So, we can write this as if this term d by V is in the order of B divided by R cube. So, C by V square, it is C divided by R to the power 6 and so on and so forth. So, for 2 body, 3 body, 4 body interactions, this can be justified from statistical thermodynamics, that actually it will corroborate to B by V plus C by V square d by V cube as 2 body, 3 body, 4 body interaction term, and we can truncate the series anywhere we need because the 4 body interaction is rare compared to 3 body, 3 body is rare compared to 2 body, and that's the idea. So, if I want the very fundamental equation, very naive sort of equation for real gases, we can truncate the series here, right, just like we can truncate the series here. So, we can write that Z is equal to 1 plus Bp by RT, real gas model for low to moderate pressure. Right. So, this is the idea of real gas, one of the very basic idea of real gas model, and alternative to that we have cubic equation of states. This virial equation on one hand, and alternatively we can have this cubic equation of state, right. So, the first cubic equation of state was introduced by van der Waals, and that is why the very basic equation with which we start this understanding of cubic equation is the van der Waals equation. So, the first one is van der Waals equation. So, you see we will not go into that exact derivation, but what we have to understand, the ideal gas form is PV is equal to RT, right. Now, volume correction, what is that? The volume, let the volume of 1 mole of gas molecules be B, right. So, the effective volume for the gas molecules to move, effective available volume for gas molecules to move is basically V minus B. So, that is the volume correction. Nextly, you see pressure. If this is the wall of the container in which you have kept the gas, and you have attached the pressure gauge here, right. Now, a gas molecule which approaches this will have a recoil and move back, right. Now, when it is hitting this wall, actually it is being pulled by the neighborhood gas molecules. So, the pressure we notice, and pressure is what? Force per unit area, and the force where from it is coming is because of the collision, continuous collision of the gas molecules with this wall of the container. And there will be a momentum exchange, and we know from Newton's second law that force is proportional to the rate of momentum change. Okay. So, the momentum exchange because of this continuous collision, and that is why we are getting pressure. So, from this picture we can understand that actual pressure of the gas will be will be higher than the pressure we are observing, because it is continuously being pulled towards the bulk, right. So, true pressure is equal to the observed pressure plus a pressure correction term. So, this is pressure correction, and van der Waals introduced this pressure correction term to be A divided by V square. So, the exact pressure is P plus A by V square, and the volume is V minus B. So, he simply corrected this pressure term and volume term in the ideal gas equation, and from there he derived this equation, right. So, this is the famous van der Waals equation for 1 mole of gas. Now, this A and B are constants, right, specific to that gas chemically. What the gas is like for oxygen, A and B will be different from that of nitrogen. So, this equation is cubic equation as P arranged, or V in terms of V. You can understand that PV square plus A into V minus B is equal to RTV square. So, PV cube minus PBV square plus AV minus AB is equal to RTV square. So, it is PV square minus PB plus PB, this will be minus, so plus RT V square plus AV minus AB equal to 0. So, you can write it as V cube minus B plus RT by P into V square plus A by P into V minus AB by P equal to 0. So, it is a typical cubic equation of the form AX cube plus BX square plus CX plus D equal to 0, and that is why this is considered as cubic equation of state. So, naturally it will give 3 roots. Okay. So, the roots we have to understand from this perspective of van der Waals equation, and what is the profile predicted for the pressure volume relation at a given temperature. So, you see from this we can write that P is equal to RT divided by V minus B minus A by B square, right. So, if you plot that with known A and B, it will exactly predict the dome and will also predict this inflection. So, this part is fine, right, though it is not exact to that of real gas, but this part is fine. However, for temperature below critical temperature, the curve looks like this. Okay. The curve actually looks like this. There is a minima, there is a maxima, and the 3 roots for a given pressure, as it is a cubic equation. One is V liquid, another is V vapor, another is V intermediate. No, this has got no physical interpretation. Right. We will try to rationalize this, but before that let us try to find out A and B. Right. So, you know that A and B easily can be calculated from this critical point data like PC and TC. Why? Because at critical point we have first derivative and second derivative of the isotherm both vanishing, right, because it is a point of inflection. So, we have at critical point state that P is equal to RT divided by V minus B minus this we can get this expression from here like del P del V is equal to what? RT divided by V minus B whole square plus 2A divided by V cube, right, and del square P del V square again we can calculate, and from there in terms of this critical temperature, right, in terms of this critical temperature upon eliminating the volume we can actually solve for A and B in terms of pressure, critical pressure and critical temperature. Like A will be expressed as a function of PC and TC, and B also we can express as a function of PC and TC, right. And the answer, as you all know, A will be 27 divided by 64 R square TC square divided by PC, and B will be is equal to RTC divided by 8 PC. So, that we can determine from this critical point property of vanishing first and second order derivatives. However, we have an easy, algebraically it is much easier method, right, and it is interesting to understand that method, right. So, you see we have the cubic equation of state. Okay. Now, the point is above and over critical point we have 3 or 2 complex conjugate roots and 1 real root. Right, complex conjugate has got no physical meaning. So, the real root is the solution. At critical points three roots are real and identical. And here, as we have discussed, three distinct real roots. Right. So, at critical point, three roots are real and identical. So, you see we can write this V cube minus at critical point B plus RTC divided by PC into V square plus A divided by PC into V minus AB divided by PC equal to 0. Right? That is the cubic form, and this should corroborate with V minus Vc whole cube equal to 0 because the three roots are real roots and identical roots, and the solution is critical volume. So, if I expand this cubic form, that V cube minus 3 Vc V square plus 3 V into Vc square minus Vc cube equal to 0. Right. So, if we just match this, we will get that 3 Vc is equal to B plus RTC by PC, A by PC is equal to 3 Vc square and AB by PC is equal to Vc cube. Right. So, if we divide this, see from here and here, I will get Vc divided by 3 is equal to B. B is simply Vc divided by 3. Okay. So, V is Bc divided by 3. So, here if I substitute that this is Vc divided by 3 plus RTC by PC. So, it will be 3 Vc minus Vc divided by 3, 8 divided by 3, right, into Vc is equal to RTC by PC. So, immediately we can conclude that Zc, which is PC Vc divided by RTC, equal to 3 by 8. So, critical compressibility factor, right, for van der Waals equation is 3 by 8. So, anyway, so obviously we can note that okay, Vc is equal to 3 RTC divided by 8 PC. Okay. So, B is equal to RTC by 8 PC because B is equal to Vc by 3, and again if I replace it here and the Vc value as this 3 RTC by P, and we will subsequently get A is equal to 27 by 64 R square Tc square divided by Pc. Right. So, you can solve it via this much simpler analysis instead of going by this first and second derivative equal to 0. Now, as I mentioned previously that we have to justify the minima and maxima. You see that below critical point we have 3 real roots. Now, here if we consider a point on the van der Waals plot here, this is a saturated liquid, saturated vapor. Now, this is not indicative of any phase change because the pressure and volume they are changing. However, what we are getting here, if I go on reducing the pressure from this or increasing the pressure, because the volume is being reduced. So, here we are having an increase in the pressure, right. We are having increase in the pressure, but still the vapor remains as vapor phase, which is absurd, right. So, we call this region as subcooled vapor. And from the liquid state, if we go on reducing the pressure, we see that there is no phase change. Reducing the volume of the liquid, still there is no phase change. Below this saturation pressure, if you go on reducing, still there is no phase change. And that is also absurd, but we call this state as superheated liquid. So, this superheated liquid arm and subcooled vapor arm, these are both metastable state. This is metastable, this is also metastable, right. So, they will collapse and forming this straight line, right. So, as they are metastable, they should collapse on each other and they will converge into the intermediate straight line. And this is further justified that for this real fluid, where we are getting this straight line, this area and this area are nearly same, right. So, technically this integral PV, this region, this is positive, this is negative with respect to this, right. So, they can be nullified, and from the physical justification we have that these two states are metastable states. So, they will collapse on each other, and from this point of view we can actually justify the minima and the maxima for this van der Waals equation below this critical isotherm, right. And not only van der Waals equation, for every cubic equation of state we will get this sort of successive minima and the maxima, and that we can justify through this understanding of these metastable states of subcooled vapor and superheated liquid. Okay. So, that is all about the van der Waals equation. The basic understanding of the cubic equations has been discussed. In the next session, we are going to discuss about the different other cubic equation of state, like this Redlich-Wang, then Schwaab-Redlich-Wang, Peng-Robinson, etc. Thank you.